started. To start off, are there any questions from last time? Procedural questions, policy questions, anything at all? Yes?
The canvas is not published yet.
Oh, okay, I will publish it. There's nothing there yet, so, but I'll publish it. Anything else? No. We strongly discourage auditing. Well, yeah.
But we asked this question from the professor. He thinks
Yeah. There is a special. Okay. Yeah. In general, we discourage auditing. If you have a very special situation, then we can allow it, but generally it's discouraged. Any other questions? Okay, today we are going to talk somewhat about applications of NLP. It will be a particularly important lecture for you because we will introduce question answering, among other things. And knowing about question answering will be important because that will be half of your project. Speaking of your projects, has everybody started looking for groups? So this is very important that you do this immediately. And a lot of you will say, well, I don't know anybody in this class. How am I going to form a group? Well, it's a class full of people who don't know anybody in the class wondering how they're going to form a group, so you just have to somehow find each other. And one way of doing this is through Piazza. So if you haven't been able to find a group, then please post on Piazza, tell a little bit about yourself, and pretty soon you'll be able to find members to form a group. Any questions about that? Okay, well, let's talk about a few applications of NLP, including question answering, and we'll start off with information extraction. Information extraction is basically the process by which you take text data, you take big volumes of text, and you extract from those relational data, like tabular data. So the input would be text and an empty relational database, and the output would be a populated relational database. So you might have text like this. You'll note that these slides were originally created during an election year in the US, but during an election year long ago. So you may not recognize all of the candidates' names. You probably recognize Clinton and Obama. You may not recognize John Edwards, who was a competitor for the Democratic presidential nomination in the United States. So you have this text here. And from that text, you can actually extract this table where you have the state, the party, the candidate, and the fraction of the votes that were received in the primary election in this state for this party. So that's what information extraction is about. It's about going from text to table. There are different kinds of information extraction. Different information extraction tasks where you're extracting different kinds of information, different kinds of relations and so on from the text. And one of these, my favorite, is named entity recognition. So named entity recognition is the process of identifying named entities. That is, things that have proper names within text. So if we go through this text, then all of these things that are underlined, Senator John Edwards, Democratic Party, Edwards, Florida, Hillary Clinton, Barack Obama, each of these is a named entity. A named entity recognition is the process of identifying these within text and associating them with a type, usually. Why would you want to do this? Why would this be an interesting task? Yes?
Get like the main ideas of the passage, which often lie behind like the names.
Okay, so the names could tell you something about the main idea of the passage, like what the passage is about. So if you've got a passage that has a lot of politicians and places, then it may be about elections. So it can tell you something about the topic of the text. What else? Yes?
So the text is basically information about several objects. So if you can extract the object out and you want to do the table, then this object would basically just be like the entries of it.
Yeah, so these would basically be entries in such a table. Why would they be useful entries?
Because you want to know more about this.
Okay, maybe you want to know more about them. You want to know, if you want to talk about what a text says about certain people, you want to know who those people are first, before you can really talk about what it says about them. Yeah. Yes?
You can associate other information with these entries, like for you have numbers and comes along things like
Right, right. So these can serve as a kind of anchor, for other information. So if we went back to this, you identify Edwards and Clinton and Obama, and then you can use these named entities as sort of anchors for this other information, like 0.14, 0.50, 0.33. So this is named entity recognition, and we'll talk more about this. There's also reference resolution or co-reference resolution. This is just reference resolution right here. And basically, reference resolution involves taking named entities. So let's say we've identified all of the named entities in a passage of text. So we take named entities and we reference them. We resolve their reference to a particular item in a knowledge base or to one another. That would be co-reference resolution. In this case, we're saying that we're identifying Senator John Edwards as this guy and also Edwards as this guy. So co-reference resolution is where you link the different mentions of the same person or place or what have you, different name mentions of the same named entity together. So here we link Edwards back to Senator John Edwards because they refer to the same person. One of the more interesting things that we might want to do in information extraction is relation detection. So here we have a relation, a member of relation. And we've identified three named entities: John Edwards, Hillary Clinton, and Barack Obama. And we've identified that each of these named entities is in a member of relation with this other named entity, Democratic Party. So relation extraction is the aspect of information extraction where you go and identify all of the instances of a relation. All of the items in a relation that you can in the text, like this member of relation. So that's a high-level overview of information extraction. Now we're going to talk about things on a more detailed level. And we're going to start off by talking about my favorite named entity recognition. And it's my favorite because it's a relatively well-defined task. You can define the rules in such a way that you know whether you're doing a good job of it or not. And so that makes it nice. It's very clean compared to a lot of other NLP tasks. So here we have a news passage from a news article, this time much more recent than Edwards and Clinton and Obama. And we have all of the named entities highlighted in blue here. President Donald Trump, Air Force, Carolina, Puerto Rico, Trump, Puerto Rico, Hurricane Maria. All of these are named entities. When we do named entity recognition, we actually want to represent these not in unstructured text. We want to represent these as items in a sequence. We want to treat named entity recognition as what is called a sequence labeling task. So we take, you can imagine it this way, and this is in fact what people do. They take and put each word, each token of the text on one line and separated from that token by white space. Then you have a label. If the item is not part of a named entity, then it gets the label O for outside. If it's the first item in a named entity, like President and President Donald Trump, then it gets a B, and then the type of the named entity. In this case, President Donald Trump is a person, arguably, and so you've got B per for president. Each subsequent token within is I and then the type. So here, down here in Puerto Rico, the Rico part gets I loc because it's a location. In this scheme at least. Could be what's called a GPE or geopolitical entity, but in this scheme that's loc. And Air Force is an org. So you've got B org and then I org. Yes?
Is this picking up the words that start with capital? So for example, if Air Force was in a smaller case, lowercase, would this be part of entity or not?
If it was a proper name, it would still be a named entity regardless of whether it was capitalized or not. So in English, it happens that in English we capitalize proper nouns, and most named entities consist of proper nouns. Although if you have the United States of America, the of is not capitalized. And yet it would still be, it still should have type, in this scheme, I loc. So it's not about capitalization. It just so happens that capitalization is correlated with being a named entity in some languages. So here are some types of named entities. So for different tasks, people use different annotation schemes for named entity recognition, and these include different types. So there's some that have 3 types, 4 types, 10 types, and some of the common types include per for person, org for organization, loc for location, GPE for geopolitical entity, FAC for facility, and NAT for natural phenomenon. So what would be an example of a GPE or geopolitical entity? What's that? Yes?
Like the president, like not the person, but like the president?
No, not exactly. Yes?
Any place where you can like find it on a map?
That's a closer approximation, but a location you can also find on a map. And yet it's different from a geopolitical entity. Yes?
Like a country or like a jurisdictional area?
Yeah, so like a country or a jurisdiction, an administrative district. You know, these are examples of geopolitical entities. A geopolitical entity is something that has a government, a population, and an extent. So anything that has those 3 things is a geopolitical entity. And if it's a place that doesn't have those, then it's probably a location. But there are some schemes, some annotation schemes, where both of those are merged together and you just call them loc. What about a natural phenomenon? Yes? Like Hurricane Katrina would be a natural phenomenon. So in named entity recognition, we only tag these when they're proper names. So if you have a person, if you say an American walked into a bar, that American is not a proper noun, and therefore would not be a named entity. So this brings up a topic that will be of great importance to you. So listen carefully. This is about evaluation. And whenever you're creating an NLP system, an NLP model of any kind, then you care about whether it's good or whether it's bad. And this is evaluation. Measuring how good your system is, how good your model is. And one of the important evaluation metrics, or pairs of evaluation metrics that are used for NLP systems, in fact, anything that you can view as a classifier, which we'll talk more about later, is precision and recall. Who here has dealt with precision and recall before? So who can tell me what these are all about? What does precision measure? Informally. Yes?
How many of the ones you thought were the case are actually the case?
Yeah, so how many of the things you hypothesize to be relevant actually are relevant? So in other words, precision goes up as the number of false positives goes down. What about recall? What is recall? Somebody else? Yeah. Yes.
Okay, ratio of the number of tokens that should have been labeled to the number of tokens that were actually correctly labeled.
So informally, what does this mean?
I guess the total number, basically the correctness of your system, like how much it's actually getting right.
Yeah, in a sense, that's also true of precision, but in a different way, right? So with recall, if we have a system that gets good recall, then it gets relatively few false negatives. So this is how I find it helpful to think about these things. You know, high recall means few false negatives. High precision means few false positives. And the formulas for calculating those are, of course, right here. There's another metric that relates to these two. And that is the F measure. Who here is familiar with the F measure? Like F1 or F2, F.5. So the F measure is basically a way of combining precision and recall scores. The most commonly used form of the F measure is F1, which is the harmonic mean of precision and recall. So that's 2PR over P plus R. So we'll talk more about that later. But basically, if you're evaluating an NER system, you'll evaluate it in terms of precision and recall and probably F1. So if we go back to these things here, if we get the right label for per, in each of these cases, we'll have 3 true positives. If we had a per here for federal, that would be a false positive. And if we had an O for force here, that would be a false negative. And so we are treating this as a kind of classification. We're classifying these tokens as either O's or not O's. And then if they're not O's, then we're classifying them according to whether they're B's and I's and what the type is. So it's a classification test. And for a classification task, then the most reasonable metrics, the ones that make the most sense generally, are precision and recall. So here's how you go about building an NER system. You start off with a collection of documents, of representative documents. And then you pay people to go through and annotate these documents, to basically mark them up, mark up all of the named entities with their types. So then you have training data. Well, after you extract all of the relevant features and you encode the data in IOB format, which is this format here. With so sometimes this is called BIO format, which I find easier to remember because it's like bio format. And besides, B comes at the beginning, and then I comes in the middle, and O comes at the end. You know, well, that doesn't make sense, but it's easier to remember. But it's sometimes called IBO notation. For what reason, I don't really know. But anyway, we want to encode things this way. So then you have training data. Yes?
What's the difference between B and I over there?
Between what?
What's the difference between B and I?
B is the first token in a span, within a named entity. Then the first one is B, and then any successive token within a named entity is I. So B is beginning and I is inside. Yes.
Like, why do you have to differentiate between these two?
Because you can have two named entities that are right next to each other with no intervening words. And so otherwise you would have no way of doing that. So you've got the training data, then you train something with it. You train a classifier. And there are a lot of different kinds of classifiers you could use. You could use Markov models of different kinds. You could use what are called CRFs, or conditional random fields. You could use SVMs. You could use LSTMs. Now people are using transformer models with CRFs on top of them. But what you get as a result of this is an NER system. A system that can do this kind of classification. So you're given a token, it can decide whether it's O or B or I. But this is not really enough. This gives us a system, but we have no idea whether it's a good system or not. So back here, when we were doing human annotation, and we got these annotated documents, we actually wanted to hold out some of these annotated documents that we can use as test data. And then we can evaluate our system and see whether it is actually a good NER system, or whether it is an NER system of evil. And we need testing and evaluation to do that. Let's talk now about relation extraction. So there are lots of different kinds of relations that can exist between named entities. Do any of you have a relation to a named entity? All of you have a relation to the named entity Carnegie Mellon University, right? Unless you're like trying to steal education, then I assume that you're in a student of relationship, CMU, right? Anybody here trying to steal education? I won't tell. But you can't audit. No, just kidding. So here are some examples of kinds of relations. So we've got affiliations, like personal affiliations, married to, mother of. Geospatial relations, like directional relations, such as southeast of, or part of relations, like organizational ones, a parent of or a unit of. And here we have their types. So all sorts of these might be interesting to us, right? Can you think of any relation you would like to extract from some body of text? What would you like to know that could be expressed as a relation between named entities? Yes.
Like if I'm given a history book, I want to extract like old map, maybe.
Like what?
If I'm given a history book, I want to extract a map like in the previous era. Like
Okay.
geospatial.
So geospatial relations. So you want to go, you want to extract all of the geospatial relations and then use this to construct a map, just based on the internal knowledge within the book. Yeah.
If I'm wanting to read about like a company, I'd look for the employees of that company, so that relationship.
Uh-huh. Yeah, that's actually a really useful kind of thing to do, and a thing that lots of people have worked on. So let's talk instead about the sorts of things we would see in 1990s or early 2000 gossip magazines, because that's after all what's really important. At the time that these slides, you could tell these slides in their, the oldest layer, they're like strata within the slides, right? They're the things I just added in the last couple of semesters, and they're things that were there from ancient times. And apparently there was a person named Brad who was married to someone named Angelina, and apparently they're no longer married. But it's treated in this slide as if it is always the case. So anyway, and Bill and Hillary are somehow still married. So if we see examples like this, Brad is married to Angelina, Bill is married to Hillary, Hillary is married to Bill, Hillary is the wife of Bill. Then we can extract two kinds of information from this, from these sentences. One is that we have these pairs, these tuples, or tuples if you're a barbarian. Like Brad and Angelina, or Bill and Hillary, that are members of a relation. And then you have these template patterns. Like X is married to Y, or X is the wife of Y. So given those two kinds of information, those two seeds, those two kinds of seeds, how could we construct a relation extractor that told us who was married to who? So you've got a few seeds like this, and you've got a big collection of gossip magazines, like the whole history of people or us or whatever, I don't know. And you want to find out all of the people that are married to the other people. How would you do it? What could you do? Let's say you want something that's really high recall, but not necessarily high precision. Yeah?
You do like pattern matching on the template, and then if there's like a name, or first do name entity recognition, and then pattern match on like name entity, and then the pattern, and then another name entity.
Okay. So one thing that you can do is use the templates. So you can do named entity recognition and use that in matching templates. And then you can find all of the people that fall into those templates. So that's one thing that you could do. What else could you do? Yes?
You could construct like a dependency parse, maybe, and search for the word married as it relates to like X and Y.
Okay. So that would be another version of the template approach, right? So you're creating a template, this time stated in terms of a dependency parse, which is something we'll get to later. And you're using that to find additional pairs of names, additional tuples that we can put into our knowledge base. Yes?
If you're just looking for high recall, you can get all the named entities in the all tuples possible.
Yeah, that would be a way of maximizing recall. But let's say we want high recall, high F1. Let's say we want high F1 and biased towards recall. We don't want like too much polyamory. We want basically to find who is married to whom. So what about, so we've only got a couple of templates here. We could make up more templates. But what if there were a way of discovering more templates? Can anybody think of a way of discovering additional templates? Yes?
If you already know that X is married to Y, but then there's a difference in other way, that could be a template too.
Yeah, so you could find other places where X and Y, where Bill and Hillary, where Brad and Angelina occur together, and you could use that to define a new template. So you could use tuples of names to find templates. And you could use templates to find tuples. So what does this suggest to your minds? Bootstrapping. So we start off, we can start either here or here. We've got some seed patterns, we've got some seed tuples. If we start off with seed tuples, we have a tuple set that we get when including these seeds. Then we do search for tuples and find patterns, extract those patterns, and that adds to our pattern set, and along with our seed patterns. Then we do pattern search and find the tuples. We extract the tuples and put those in our tuple store, and also put them in our tuple set. And we use them to do more tuple searching. And so on around the circle. What could possibly go wrong? What could go wrong?
If you start with something that's not quite right, you can just end up with garbage the whole way through.
Yeah, so you have an error propagation problem, right? And if you end up with, you could end up with some patterns like Brad hates Angelina, and then every time you come across that pattern, you assume that X is married to Y. Where, the fact that they hate each other is completely orthogonal to whether they're married or not, one assumes. So this is a low precision kind of approach, but relatively high recall. So let's talk about information retrieval. We're not going to talk about this too much in general. There's a whole class about this called search engines. Has anybody taken search engines? Yeah, you took search engines? Was it hard?
There's a lot of information.
A lot of what?
A lot of information.
Yeah. So this is not going to have a lot of information in it. Not a lot of information to retrieve. But we are going to talk about something that is really important to you. And this is the vector space model of documents. So we can, words are nice, right? Who likes words? I like words. Do computers like words? No, computers like numbers. And computers especially like real valued numbers. Not that much because of buffer overflows and things. But they do really well with real-ish kinds of numbers. And so it would be really nice if all of these words and stuff were just numbers. And one way of representing documents as numbers is to represent them as vectors. So we can have a document as if we have a vocabulary of sigma, then we can have a document represented as a sigma dimensional vector, where each dimension in the vector is the number of times that a word occurs. So for each word in the vocabulary, there's a dimension in the vector, and for each of those dimensions, then the number of times that word occurs in the document is the value of that vector at that dimension. So we can represent documents in this way. We can represent queries in the same way. Just think of a query as a little document. So this is what is called bag of words. Who here has heard of bag of words before? Yeah. So you can give a bag of words representation to each document in your set, and you can give a bag of words representation to a query, and then you can look at the similarity between the query and the documents. How would you, so each of these is a vector, right? A document is a vector, a query is a vector. How would you say how good a match a query is for a particular document? In other words, what is the similarity metric that you might use for quantifying the similarity between two vectors of this kind? Two bag of words vectors. Could you use the dot product? I mean, that quantifies how similar vectors are, right? What say you? You're saying no? What?
You can create a matrix that represents like all the vectors and what they hold, and gives the information about like which particular vector you're looking at, like by the column or something.
Yeah. I'm not exactly sure I follow what you're saying. How would you combine all of that together and get a number that indicated how similar or different two vectors were? So could you use the dot product? Yeah.
Could you use the angle between the two vectors?
Okay, so you probably want to use the angle between the two vectors rather than using the dot product. Why would you not want to use the dot product?
Because the document would likely have a lot more words than queries. It would have a greater magnitude.
Right. So with the dot product, it's sensitive to the magnitude of the vector, and so you end up being sensitive to the number of words in the query rather than just to the ratio of the different kinds of words to one another. So you would use the angle between the two vectors. And we have a way of computing this. What do we call the metric that corresponds to the angle between the two vectors in this kind of situation? This is a cosine, right? So this metric we call cosine similarity. And this is going to be your friend. You're going to love cosine similarity by the time you're done with this course. You're going to think cosine similarity is the answer to all of your questions. Now, it's not quite the answer to all of your questions, because you have to do some other things in order to get cosine similarity to work for you in this situation. Because of the fact, for example, that some words are really frequent, like the. And if you have the in a query, and the in a document, how meaningful is that the? I mean, the is frequent in any document, right? Any document in English has lots of the's in it. So how much should that the be weighted in terms of choosing the best document for a query?
0. 0.
It should be weighted very low. Is that what you're going to?
Yeah.
Yeah. So we have this measure called TF-IDEA, which is term frequency inverse document frequency, which basically is a way of weighting words so that that being frequent in a small number of documents makes the word big, and being frequent in a lot of documents or infrequent in a lot of documents doesn't have that same kind of contribution. So it's basically the count of the word W sub j times the log of the number of documents over the number of documents with W sub j. So it's the term frequency multiplied by the log of the inverse document frequency. So information retrieval is another place where we can apply precision and recall. And information retrieval brings us to a specific information retrieval topic, which is question answering. So here is a general question answering architecture. Pay close attention, because when you're developing your question answering architecture for the project, you will 4 times out of 5 probably start with something like this, and then build on it, innovate beyond it, and so on. So you start off with a question, and you take that question and you change it into a query. That is, you represent it as a vector. But you also classify that question. Is it a yes-no question? Is it a WH question? If so, is it a who question, a where question, a when question? And you keep that information for later. Then you have a bunch of documents. Now in your project, you're just going to have one document, so you don't need to worry about this. But in real life, then you have a bunch of documents and you've indexed them in some way that will allow you to do to apply this query in an efficient, computationally efficient way. So you get back a set of relevant documents. And from these, you retrieve the relevant passages. So how do you get back the relevant documents? What tells you that the documents are relevant? Cosine similarity, probably TF-IDF weighted cosine similarity. And so you have the documents, you divide the documents into passages, and then you retrieve the passages that are relevant. Well, how do you know which passages are relevant to the query? Yes? Yes.
You have to reweight it.
TF-IDF weighted cosine similarity. So you got the passages that are relevant to the query. Then you go and do answer processing. Yes?
I have a generic question, but how big and generally would a passage be considered?
Usually a sentence. Maybe something a little bit larger than a sentence. But in question answering, it's usually like approximately a sentence. So we've got this passage, but a passage is not an answer to a question. It's just a passage. So we want to extract from that the answer. And we can do this if we know what kind of question the question was. What kind of information it's asking for. Because we can use things like named entity recognition. If we're looking for the name of a person or a place or an organization. So we take these passages and that classification as an input, and we yield an answer. So basically, every one of you is going to replicate in some form this, this system diagram. So pay close attention to it. Of course, when you do it, it's going to be more like this. So we've got the question, we've got question formation, question classification, and then this goes to a known document, because you'll just have one document, plain text. And you'll retrieve the appropriate passages or passage from that document, then process it, then get your answer. Questions about this? Yes?
So usually the questions are generated by this system, or we have the data with questions, or questions are generated?
So the questions, the question is, where do the questions come from? And in the, so there are two parts of the project, right? There's a question generation part and a question answering part. So in the question generation part, you'll be given known documents. You'll be given documents, and you'll have to generate questions on the basis of those documents. Questions about those documents, questions that can be answered based on those documents. And based on this, we'll generate a whole bunch of questions. And you will evaluate those questions as a class. You'll evaluate those questions and say which are the good questions and which are the bad questions. And then the best questions will go on to serve as the input to the question answering portion. So we will submit those questions to your question answering systems and see if you can answer them. And then we'll get back the answers, and again, you will evaluate, in a blinded fashion, the question answer pairs that we get from that output on a number of different criteria. Things like whether the question is accurate, but also whether the answer is accurate, but also whether the answer is fluent and concise, and so on. Yes.
What's question classification?
Question classification is basically classifying a question as to whether it's a yes-no question or a content question. And if it's a content question, what kind of content it's asking for. Although there are other kinds of classifications that could be useful as well. It's basically just classifying questions in ways that would be useful for extracting answers to those questions.
So will it have its own classifier and architecture to classify questions?
You'll probably have a question classifier within your architecture. I would say pretty much all successful systems have something like that. Yes?
Do you have any way of like evaluating the correctness of an answer in this system?
Do
we have any way of evaluating like how correct different answers are in this system?
in which system are you talking about?
Like this question answer system.
So in this, it doesn't include evaluation. So there's no automatic evaluation, certainly, of how accurate questions are. But in practice, you would have evaluation that tied this and this together. You would hire people and they would evaluate whether the answers are correct answers to the questions based on the documents. In our case, then you will be the evaluators. So there will definitely be evaluation of whether the questions are accurate or not, because you will have to read the document and then say whether the system correctly answered the questions. The documents, I should say. Although, hopefully, each of you will not have to read more than one or two documents for the evaluation. So to evaluate question answering, we use a metric called mean reciprocal rank. It's a pretty simple metric, pretty simple idea. So yes, it's simple, and now I'm having a hard time explaining it. So basically, you're looking at the rank of the first correct answer to the question. 1 over the rank of the first correct answer to the question. So the farther down the list you have to look in order to find the correct answer in terms of the number of answers that are returned by the system, then the worse it is for this metric. So it's just basically taking the mean of all of these for a system. And that is the mean reciprocal rank. So a good system is one where the right answers are relatively high ranked. Yes?
What's like the general criteria for, is it mainly just content or is it grammar?
In this, for mean reciprocal rank, if we're talking about this, then it's content. For our systems, where we will not use mean reciprocal rank because you'll not rank the answers. You'll just give an answer. And in our case, then we will use grammaticality as one of the criteria. Fluency, we would say. And in some evaluations, other evaluations of question answering, then that also enters in, you know, the fluency of the questions and not just their factual accuracy, or of the answers and not just their factual accuracy. So here are some ideas that have come up in this lecture that probably will come up again. One is supervised classification. This we talked about when we talked about named entity recognition. So what makes classification supervised? What is supervised machine learning? Yes?
If someone is manually checking the output, so you're grading the output you're giving it a graded data set.
Okay, you're giving it a labeled data set,
Yes.
right? So it means that in this case a classifier or some other machine learning model is trained with labeled data. That it's supervised with labels that were added by some human somewhere. That's supervised machine learning, and in this case, we might be talking about a classifier as the kind of machine learning algorithm that we're talking about, and one kind of classifier is a supervised classifier. So what's called a naive Bayes classifier is supervised, or an SVM, or support vector machine, is a supervised classifier. And these are to be contrasted with unsupervised classifiers, which are basically clustering algorithms. So there's also the idea that will come up again and again of feature vector representation. So make sure you're comfortable with this because it will come back to you on the project, on the exam, in homework, etc. What is the main idea here? Why would we want to represent things as vectors? Yes? Yeah, so we can, it's easy to quantify how similar two vectors are to one another. So if we represent two things as vectors, then we can talk easily about how similar or different they are from one another. What about bootstrapping? I usually ask a question on the midterm about bootstrapping to see if you're listening to this lecture. So I might do that again. So what is bootstrapping, or what is an example of bootstrapping from this lecture? Yes?
I guess you said using templates to find more templates.
Yeah, basically. So you start off with some kind of seed, and you use that to find more instances of that same thing. So in the relation extraction example, then you're using templates to find more tuples, to find more templates, to find more tuples, and it's a nice example of bootstrapping. finally, there's the subject of evaluation. And there's pretty much always, either on the midterm or the final, a big question about evaluation. So this is something you definitely need to know about. And the first thing to know about is precision and recall. And it's also good to know about mean reciprocal rank. But precision and recall are going to come back again and again. So tell me again, what is precision in an intuitive sense? You don't need the formula. Yes?
When you have high precision, you have like fewer false positives.
Yes, high precision means fewer false positives. High recall means fewer false negatives. Yeah. Okay, so if you got all of this stuff, then you're in good shape so far. If you have any questions, now is a good time to answer because we have a few minutes. My voice is not yet given out, so I can still answer questions. Yes?
Can you give another definition of bootstrapping? Kind of out of that example of tuples and templates and tuples.
You mean...
Can you kind of further elaborate what bootstrapping is?
So bootstrapping is where you start off with a small number of seeds. So you have, rather than having a lot of labeled data, you have a small number of labeled seed data or templates or something else that you can build on. And you have some way, some kind of feedback loop where you can get more of those by using those. So you can get more seeds by employing your seeds.
So is that a way to, is that kind of form of data augmentation?
Or
not?
Data augmentation can take the form of bootstrapping. Yeah. Any other questions? Shahan?
The questions generated in the project, are they like simple enough that you can answer them based on explicit information in the text? Or you have to infer it?
They have to be answerable based on information that's explicitly in the text. So, otherwise, I mean, people in the class who do the evaluation would have no way of evaluating them. If it requires inference, there's not a reliable way of doing the evaluation if it requires inference beyond explicit information.
So for example, if the text says, he sold a book to David for $20.
Uh-huh.
The question is, how much money does he have? Like it's not, like it warrants that you know what selling means,
Uh-huh.
but it's not explicitly clear.
So that would be so if the answer was how much money did so-and-so get from David or whatever, then it might be okay, but in general that sort of question would not be okay. That requires too many levels of inference, and it is sort of out of bounds of the project as we see it. There are question answering data sets that exist, that explicitly involve multi-hop reasoning, or are supposed to, although it's arguable whether they actually do. And in those cases, on those data sets, then you would have to do some kinds of inference. But they're usually inferences that don't require much world knowledge. They're inferences that require only knowledge that is present within the document. Does that answer your question? Other questions? Yeah. Oh, no, not a question. Stretching? Anything else? How comfortable are you with the question answering system diagram that we showed up there? Let's say with this. Yes.
Is the question answer system we're going to build supposed to generate multiple answers for a single question? Since you're using
We won't use mean reciprocal rank in evaluating it, and you will generate just one answer. So in a normal question answering system, like back here, you have the passages, and for each of these passages you probably get an answer. And these passages are ranked according to their relevance to the query. So that one answer is the best answer according to the query. There's a second best answer, a third best answer, a fourth best answer, and so on. So all of the answers that come out here are ranked. So with mean reciprocal rank, it's that rank that we're talking about. It's the rank. So you go down this list for each answer. You go down the list until you find the first correct answer. And that's this number here. Does that make sense? Any other questions? Yes. No. But what so if there is no correct answer, then essentially the rank of the first correct answer is infinite. In practice, I think that people usually have long enough lists of passages and answers that the correct answer is typically found somewhere in that list. It's just that it's not undefined if the answer is not, if there is no correct answer in the list.